Hi. In the previous videos, we saw how three-dimensional functions look like. And now we are going to learn how to calculate derivatives of such functions, and then later we're going to generalize it to the case when a function has n different variables. So look, if we are going to calculate derivatives with respect to two different variables, because now the function has two variables, we're going to call them partial derivatives. Okay, so now we've got a function z is f of x and y. So look, now value of z depends on one hand on x and on the other on y. Okay, so in this case, calculating derivatives might be a little bit tricky. But let's remember, what did we do when we calculated derivatives of just one function alone? A function of one variable alone. Look, and let's consider a case like this. Let's just say that the only thing that is changing here is x. So, at the beginning, of course, we want to know what is the impact of changing x on change in z. So what we are doing over here is that we are actually calculating a difference quotient, just like we did before. And look, how will this difference quotient look like? Look, we are assuming that y is constant. So we will have here f of x0 plus delta x y0 minus f of x0 y0 divided by delta x. Look, what do we see that happens over here? X has changed by some amount, and as a result, value of the function changed, right? Because we went from point x0 y0 to point x0 plus delta x y0. But look, what does this specification implies? In this case, we see that y is constant. Now, but look, if this is the case, this means that over here we can calculate more than one difference quotient. So the second one would be what is happening if y is changing while x remains constant. So we will have f of x0 y0 plus delta y minus f of x0 y0 all divided by delta y. So in this case, of course, we've got that x is constant. So look, what we are doing with these two different quotients is we are trying to assess impact of changing x on y. Of course, here, what we would calculate is an average impact. So, by how much z changes when x is changing by 1 unit. And lower, by how much z changes when y changes by 1 unit. Okay, so we see that what we can do when z is a function of two variables is that we can actually separate impact of those two variables on z and calculate each of them separately. But look, we said before that using difference quotients is not very accurate. You know, of course, if this would be linear function, not a problem. But if the function is wavy, it has convex and concave part, using a difference quotient is not very accurate. So, what do? We can calculate limits of these difference quotients. Okay, and look, this is exactly how partial derivatives are defined. So if I'm going to calculate limit with delta x approaching 0 out of delta z, delta x, I'm calculating limit with delta x approaching 0 out of f of x 0 plus delta x, y 0 minus f of x 0, y 0 over delta x. And this, by definition, is the partial derivative of z with respect to x, which, assuming that z is a function of x and y, we can write either as dz dx or, I'm sorry, f x. Look, let's notice two new things over here. First, just in notation, instead of writing d like that, to separate it from the case of a function of one variable, we are making this more wavy shape, but we are still reading it as d. And now, or if we want to use this notation, look, before, instead of writing f with prime, because when we had function of one variable, that was sufficient. Now we are writing it like that. Okay, so we've got, and now that we've got this covered, we can right away say, write down from the definition how we calculate the derivative of z with respect to y. It is going to be limit with delta y approaching 0 out of difference quotient delta z delta y, which is limit with delta y approaching 0 out of f of x0, y0 plus delta y minus f of x0, y0 over delta y, which we can write as dz dy or f of y. Now, remember, because this is actually the entire key to calculating partial derivatives. If I calculate partial derivative with respect to x, y is at the same level, which means y is kept constant. And over here, x is still at x0, so x is kept constant. Okay, and look, actually, this is basically all that we need in order to be able to start calculating partial derivatives. Now, let me show you with a couple of examples how it is done. Okay, so let's say that z is 3x squared plus xy plus 4y squared. Okay, look. Now, when I tell you calculate derivatives, it means I want you to calculate both. First, dz dx. Okay, so look, let's go component by component. Rules of differentiation are exactly the same as before with function of one variable, we just need to remember, when we differentiate with respect to x, we are imagining that y is a constant, that it's a number, like 7, 3, or square root of 5. So, out of this, we are getting just 6x. Now, y is treated as constant. So, xy is like 2x, 3x, 7x. We are getting just y. And look, over here, y is treated as constant. So this expression is treated as constant. So it is equal to 0. And we are done. We've calculated first partial derivative. Now, let's move to the second partial derivative. dz dy. And look, now x is treated as constant. So this whole thing is gone. Now we've got yx, where x is treated as constant, so the derivative is just x. And out of this part, we are getting that this is 8y. And this is it. This is how we calculate partial derivatives. Okay, now let's get to a couple, let's just say, more demanding examples. But it's, as you will see, it's all really easy. Okay, so we've got x plus 4. It times 3x plus 2y. Look, I'm choosing this example because now let's practice also differentiation using a product rule. Okay, so if I'm calculating the derivative dz dx, what do I need to do? Look, of course, I can treat it as two functions, separate, and I need to use product rule to calculate. So first, derivative of the first one, which is just 1, times the second one, which is 3x plus 2y, and now plus the first one, x plus 4, times derivative of the second one. And look, out of this, because this is constant, we just get that this is 3. And of course we should calculate it, but this is not the point of at the moment. And now look, if I'm going to calculate and now the same function, but using but with respect to y, x is kept constant. So now look, derivative of this is 0 times this, still 0, right? Then plus the first function, and this is kept constant, so 0, and we get just 2. Okay, so let's try another example, just to make sure that we are understanding everything properly. And let's see what happens. Okay, so now our task is z equals 7x plus 6xy squared minus 4x to the power of 3. Okay, so dz dx is equal to 7 plus 6y squared minus 12x squared. Now, dz dy, 0. Out of it, we get 12xy, right? 2 goes up front. We are just differentiating this part. And 0 out of this. We're done. Okay, maybe one final example. Now for the quotient rule. So z is 5x squared plus 3 divided by 1 minus 2. Okay, and again, let's start with dz dx. So, from the quotient, in the denominator, we just take this expression, take it to the power of 2. Now, over here, we first differentiate this, of course, with respect to x. So we get this is 10 function at the bottom, which is y minus 2. And now, minus, and now minus, and we leave this function at the top the way it was, and we differentiate the function at the bottom with respect to x, which actually is 0. So look, our outcome is simply that. But look, we see that those two cancel each other out. We get that this is 10x over y minus 2. And look, why am I doing this like that? Let me just show you that actually, even though here quotient rule is implied, we don't need to do it. Look, how I can think of this function different. Look, this is the same as 5 over y minus 2 times x squared plus 3 over y minus 2. And now look, if I'm differentiating this expression with respect to x, this whole thing is constant, right? So, what should I do? I should take 2, put it up front, and I'm getting that this is 10 over y minus 2 times x, and this is gone in differentiation because it's a constant. Right? So, as you see over here, I was able to calculate it in a way easier fashion. But of course, this requires a little bit of practice. Once you start practicing more, you will be able to do it very, very fast. Okay, so now, of course, we can differentiate this also with respect to y, and how much are we getting from this? So this is, again, we're starting with the with our rule, so we got y minus 2 squared, and then derivative of the first one, which is 0, times the second one, which is 1 minus 2. But of course, this is going to be just 0. And then we've got minus, first one, so 5x squared plus 3 times derivative of y, which is 1, which gives us negative 5x squared minus 3 over y minus 2 squared. Okay, so look, at this moment, we know what are partial derivatives and how to calculate. The only trick we need to remember is that when we differentiate with respect to one variable, we simply treat the other variable as a constant. Okay, so what else can we do right now? And look, when we were calculating derivatives before, we were calculating first derivative first, but then, for example, when we wanted to optimize the function, find a maximum or minimum, we calculated second derivatives. And this is what we're going to do right now, because for now, we were calculating partial derivatives, but those were first partial derivatives. So now let's go to second partial derivatives. Of course, we could go deeper, but we will not have to. Okay. So, look, when we were calculating second derivative, we were just calculating derivative of a derivative, right? Not very complicated. So here, the situation is a little bit more involved, because look, I can differentiate z with respect to x and with respect to y, which actually tells us that each of these derivatives I can also differentiate with respect to x and with respect to y. So if this is a possibility, why not try it? Okay, so let's start it like this. Second derivative of z, as you see, all the symbols will be the same. Z with respect to x. Now we will have x squared, or the other notation for this is simply f(x), x. We took the function f, we differentiated with respect to x for two times. Just remember, we are still dealing with z equals f of x. So, let's look. I'm going to write that a little bit later because I want to show you a point. Like, how do we get this derivative? Look, I'm simply taking the first derivative with respect to x and I'm differentiating it for the second time. Those two are so as a result, I'm obtaining expression like this, which of course by definition, of course, is f(x), x. So in this case, we differentiated with respect to x twice. Now, but this is not all that I can do. Look, I can also calculate second derivative of dz dy, and look, I'm going to obtain there dy squared, and this is the derivative with respect to y right? So I would just take this derivative, differentiate it again with respect to y, and I can write it as f y y. Look, but this is not everything I can do, because I can also calculate mixed or cross derivatives. Okay, so how is this done? Look, I can take derivative of, let's start actually from this expression. Look, I can take derivative of z with respect to x, and I can differentiate it with respect to y. So what I'm going to get as a result is going to be d squared z dy dx, or equally I can write it as dfyx. And look, by the same token, I can take derivative dz dy and I can differentiate it with respect to x. Where am I going to get that? Well, I'm going to get that dx dy fx y. Okay, so look, we see that in this case we can actually calculate 4 different derivatives. So let's do it. Let's just say for this example that we have on the blackboard over there. So look, first I'm going to calculate d squared z dx squared. So I'm calculating derivative of this derivative with respect to x. It turns out that this is negative 24x. Then let's just say that I'm going to calculate derivative dy square z dy squared, and I'm differentiating this derivative with respect to y, and I'm getting that this is just 12x. Okay, now I want to differentiate the derivative at the top. So dz dx with respect to y. And what am I going to get now? So I'm getting that this is just 12y. Right? Now, if I'm going to finally differentiate the derivative with respect to z, this derivative of z with respect to y, now with respect to x, I'm going to get that this is 12y. Let's notice very simple, a very pleasant surprise that we got here. Look, as it turns out, those two derivatives are equal to one another. Is it a coincidence? Well, of course, coincidences are something that happen, right? But in mathematics, it's something that happens very rarely. And if we've got those two derivatives equal to one another, maybe this is a rule. And actually, it is a rule. This rule is called the Young's theorem. Basically, what Young's theorem says is that cross derivatives are equal to one another. Look, we can write it like this, or in an equivalent form, we could write just fxy, fyx is equal to fxy. Right? It doesn't really matter. Those two means the same thing, it's a different notation. Okay, so basically what Young's theorem says is that if I differentiate a function with respect to x and then with respect to y, I will get the same result if I differentiate a function with respect to y then with respect to x. Now, can we prove it? As it turns out, with a lot of things, the proof here is basically self-evident and it's hidden in the theorem itself. Look, dz dy dx d squared dz dy dx is the same as d dz dx. And this is the same as g, for example, square z times okay, look, what I'm going with this, because if I multiply the two components in the denominator, it doesn't really matter in which order I am multiplying. Okay, let's do it in two steps. I wanted to do it too fast. Okay. So I can switch their order. Now, if this holds, this, by definition, is the square z dx dy. And we see that it is done. And look, again, it turns out that if we interpret derivative as a ratio of two differentials, because look, this again are differentials. they are just partial differentials. Part of the total differential that we are going to discuss a little bit later. But by that we are able to prove the Young's theorem. Okay, so now you know that actually when we are calculating second partial derivatives, we need to calculate just 3, not 4. Because those two will be different. Well, they don't need to. We might have a case, and that would be coincidence when they are equal to one another. But those two are always going to be equal. So if you have one, you don't need to calculate the other. Okay, so the only thing left now that we know how to calculate second partial derivatives, first and second, is to generalize our knowledge for the case when we are dealing not only with function of 2 variables, but with a function of n variables. So now let's imagine that y is a function of x1, x2 until xn, when n is some finite number. Some positive integer, but very, very big. So we have a finite number of variables in the function. Okay, so in this case, how can I calculate derivative dy dx1, or for short, f1? Well, I would do it like this. By definition, this would be a limit with delta x1 approaching 0 out of the difference quotient delta y, delta x1, or in other words, this would be a limit with delta x1 approaching 0 out of the expression f of x1 0 plus delta x1. Look, I needed to add another subscript, right? This is not delta 10. Okay, let's put here a comma so we know that those are two different things. So this is value at the beginning of variable x1. Okay? So here we have x2 0, and we would go on like this until we would get up until x and 0, and minus the initial value of y. So x1 0, x2 0 until xn 0, and all divided by delta x1. Okay, this is like this is some specific formulation, but what can we notice over here? Look, again, only one variable is changing. x1 is changing, but at the same time, x2, x3, x4 until xn is constant. So, if I want to make like a more general indication of what would happen over here if I want to differentiate this function with respect to variable xi, which I would denote as fi, that would be limit with delta xi approaching 0 out of difference quotient delta y, delta xi, or limit with difference quotient of limit with delta xi approaching 0 out of difference quotient. And this one is going to be a little bit longer. So it would be f of x1 0. fx to 0 until we would arrive at some xi 0 plus delta xi, and then again we would go like this until xn 0. Then we've got minus f of x1 0, x2 0. We go on like this until xi 0, and then until xn 0. All of course divided by delta x. Okay, so look, so basically the rule of differentiation, finding partial derivatives remains the same. The only thing is that now it is becoming slightly more involved. But remember, in this case, x1, x2 until xn, but without xi are, oh actually, I'm sorry, here should be r. They are constant. Xn is constant, but they are all constant, so r constant. Okay, now how about second derivatives? Look, again, we can calculate second derivatives in exactly the same fashion. What does it mean? Now I can take first derivative and differentiate it with respect to x1, x2, x3, x4 until xn. Then I can differentiate derivative delta dy dx2 with respect to x1, x2, x3 until xn. And look, here there is some very specific pattern that I would like you to actually see on how many partial derivatives we can calculate. How many second derivatives we can calculate. Look, if I've got y equals f of x, let's make then I can calculate one derivative dy dx and one second derivative dy d square y dx squared. Okay, so in principle I can calculate here a total of one second derivatives. Now if the function changes to z or y equals f of, no, let's keep it consistent. Z equals to f of xy. Now, I can calculate here two partial derivatives, dy, dz, dx, and d, z, dx, and dz, dy. And look, imagine it like that. Now, because this actually is going to be important for us a little bit later. Imagine that I'm going to create here a matrix or a determinant. Doesn't matter. And look, let's just say that each row of this matrix represents a first order partial derivative. So first derivative here, dz dx, dz dy. Now, I can differentiate each of these with respect to x and y. So, over here, I will have d squared z dx squared. Over here, d squared z d y dx. Over here, d d squared z dx dy, and over here d squared z dy squared. And of course we remember by the Young's theorem that those two are equal to 1. But look, this time we can get a total of 4 derivatives. Right? Okay, now what if we go further? If I go now to function z equals f of x1, x2, y is equal to f of x1, x2, and x3, and look, how many derivatives I can calculate? I can calculate f1, right? f2, f3. Again, look, if I have those derivatives over here, and I want to put them into a determinant, and so here would be derivative f1, here f2, here f3. Remember, so this is partial derivative with respect to x1, with respect to x2, and with respect to x3. I can differentiate each of them with respect to x1, x2, and x3. So, what will I get as a result? Look, here I will have derivative f1, here f2, and f3, Here I will have f1, 2, f2, 2, f3, 2. Over here, f1, 3, f2, 3, f3, 3. Total of 9. And again, let's notice a very simple thing. Those two partial derivatives, by Young's theorem, must be equal to the same value. Those two derivatives, by Young's theorem, must be equal to the same values, and those two derivatives, let me just make it like this, are also equal to the same values. Okay, so now let's figure out if we would have f a function y equals to f of x1, x2, x3, and x4, how many first derivatives we can have? Well, we can easily calculate. This is going to be 4. But now, how many second derivatives are we going to have? Well, 16. Why is it like that? Because look, in the first case, I could calculate first derivative. So for that one, I could just calculate 1 second derivative. Here I could calculate 2 derivatives, first derivatives, and for each of them, I could calculate 2 second derivatives. Here I could calculate 3 first derivatives, and for each of them, I could calculate 3. I could differentiate, and for each of them, I could calculate 3 second derivatives. So here we've got 4 times 4. So look, in our case, here, when we have a function of n variables, we can calculate total of n to the power of 2 second derivatives. Okay, but look, I just wanted to show you the rule will not, in examples that we are actually going to do, we're not going to go beyond the case with 3 variables. But of course, I want you to know how it works, and we can actually go as far as we want. Okay, so now that we've learned how to use partial derivatives, we are ready to find maximum and minimum and saddle point as well of first 3-dimensional function and then of n-dimensional function. Thank you very much for your attention.